Let's get started with chapter 2. In this chapter on the kinematics of wheeled mobile robots, we'll first focus on understanding some essential aspects of wheeled mobile robots kinematics, and then we will show the derivation of the kinematic equations of a number of wheeled mobile robots. Degrees of freedom, or DOF, of a rigid body is simply defined as the total number of freedom of the rigid body minus the number of constraints on the motion. In the absence of constraints, a single link on the plane has 3 degrees of freedom: translational movement in the x direction, translational movement in the y direction, and rotational movement around the axis perpendicular to the plane constitute the degrees of freedom of the link. The constraints on the motion of the rigid bodies often come from joints. If the link is connected to the ground with a revolute joint, 2 movement constraints are created. It is not possible to move the connection point of the link to the joint in the x and y directions, neither at the moment shown nor at any time. So this is a geometric and permanent constraint. And as you can see, we can write this constraint as x equals 0 and y equals 0. The number of degrees of freedom of a mechanism is determined by the number and type of the joints and associated kinematic constraints. Robotic arms are usually made of revolute and prismatic joints that have 1 degree of freedom. As we have seen on the previous slide, a 1 degree of freedom revolute joint creates 2 constraints in the plane, and in 3-dimensional space it creates 5 constraints. For an arm robot, by counting all the degrees of freedom of the links and subtracting the number of constraints of all joints, the number of degrees of freedom is obtained. DOF of a serial arm robot are always equal to the number of joints. All the constraints imposed by the joints are geometric, and we call this kind of constraints holonomic. The degree of freedom of the shown robot is 3. Q1, Q2, and Q3 are the joint variables. So what can we say about DOF of wheeled mobile robots? These kinds of robots are composed of a chassis, which is the main link, and some wheels. Let's first take a look at constraints imposed by wheels. If you consider a standard wheel in plane rolling without slipping at an angular velocity psi dot, the velocity of the center of the wheel will be psi dot times r, where r is the radius of the wheel. This velocity is in the longitudinal direction and is located in the plane of the wheel. Each standard steerable wheel imposes in system a non-holonomic constraint, since it does not allow normal translation to the rolling direction. In that Vn equals 0. In the other words, the wheel rolls on the ground without slipping longitudinally nor skidding sideways. Let's express this constraint mathematically. If the wheel does not impose any constraints, we can get the speed of the projection of the center of the wheel on the ground with these relations in an inertial coordinate system. Here is the components of the coordinate system, x and y, and you can see here the x dot and y dot. X dot equals vt times cosine of theta plus vn times cosine of theta plus pi over 2, and y dot equals vt times sine of theta plus vn times sine of theta plus pi over 2. If there is no motion in the normal direction, Vn equals 0, so Vn is omitted in these equations. If we and we obtain these equations, and if we remove Vt from these equations by a simple algebraic manipulation, finally the constraint equation will be in this form. In fact, this equation is not integrable, and this kind of constraints are called non-holonomic constraints. This constraint is not on position of the wheel. Compare it with these constraints. These constraints are on the position, but this constraint is on the velocities. It is a mobility constraint, and we will talk about this more in the next slides. As we have seen, the constraint caused by the wheel is a non-holonomic constraint on the feasible velocities of the wheel. So what does it mean? To answer this question, consider a robot that has two wheels enforce these constraints. It's true that the robot cannot instantly move sideward, but by performing some maneuvers, it can finally achieve a new x and y located on its lateral side. These maneuvers can be the ones we do in parallel parking. Therefore, this non-holonomic constraint does not reduce the degree of freedom, but because it is not possible to instantly create velocity in the lateral direction, it reduces the mobility. So the constraints on the wheels reduce the mobility, but not the degrees of freedom of this robot. What can be said if the wheels were omni wheels? Please think about this. In summary, the number of degrees of freedoms of a ground land-based wheeled mobile robot is the number of scalar parameters required to describe the motion, that is velocity, of the main link of the wheeled mobile robot, which is chassis. The maximum number of DOFs of a wheeled mobile robot is thus 3, x translation, y translation, and theta rotation. And the number of wheeled mobile robot DOFs at any instant may depend upon the steering angles of the wheels. The configuration space, which we often call the C space for short, is the space of all configuration of the robot. The number of degrees of freedom is the dimension of the C space, or the minimum number of real numbers we need to represent the configuration. For example, for this simple planar robot that has two joints, the configuration space can can be represented as shown. Q1 and Q2 are configuration space components. If these joint variables vary from 0 to pi multiplied by 2, the configuration space will be a square. It is worth noting that here we are actually dealing with a plane instead of a space. However, in robotics, the term C-space is commonly used. Every point inside this space corresponds to a configuration that you see its mathematical representation and also physical representation. So this is a representation of physical representation of a configuration, and this is mathematical expression. And here you can see the C space configuration space of the robot. If we only had two links without joints, we would need 6 parameters to represent their configuration space. 3 parameters for each link. When these links are connected to each other and to the ground by joints and form a robot, the representation of the configuration space requires 2 parameters, namely Q1 and Q2. These joints have imposed holonomic constraints and decreased the dimension of configuration space as well as the number of degrees of freedom to 2. So we can say that holonomic constraints reduce the dimension of the C space. It should be noted that in the case of this robot, the number of degrees of freedom is equal to the dimension of the configuration space, which is 2. Now consider the chassis of a mobile robot driving on a plane. If we define an X and Y reference frame, we can represent the configuration of the chassis as Q equals X, Y, and theta, where theta is the heading angle of the chassis and X, Y refers to the location of a reference point on the robot, which is here, and here you can see the reference point. There are velocity constraints between wheels and ground, which we know that they are non-holonomic and reduce the speed of possible velocities of the robot. However, these constraints do not reduce the dimension of configuration space. As we have seen, sideways motion can be achieved by parallel parking, and the robot can reach any configuration in the three-dimensional space. We can also add in the parameterization of C space the rolling angle of wheel. Psi is the rolling angle of the wheel, and we can also add it here. Yeah, that's it. Therefore, the configuration space of a wheel can even be considered as four-dimensional. Here is another example where the configuration space is four-dimensional. Phi is the steering angle for the front wheel. We can add in parameterization of C space also the rolling angle of each wheel. In summary, it should be said that non-holonomic constraints such as constraints that conventional wheels impose do not reduce the dimension of the configuration space as well as the DOF. Moreover, steerable wheels increase the number of C-space dimensions. In the previous slides, we talked about degrees of freedom, but since it is a mobile robot, the maneuverability will come into a picture. Maneuverability of a robot chassis is its ability to directly move in the environment, which is the result of, one, the rule that every standard wheel must satisfy its no sliding and pure rolling constraints, and degree of mobility, delta M, is determined based on this rule. And second, the additional freedom contributed by steering and spinning the steerable wheels, degree of steerability, delta S, is determined based on this. Mathematically, mobile robot maneuverability is defined as the sum of degree of mobility and degree of steerability. So here, delta M, in which M is uppercase, shows the degree of maneuverability, and delta M, in which M is lowercase, shows the degree of mobility. We will talk about degree of mobility and degree of steerability in the next slides. Degree of mobility equals degree of controllable freedom based on change in wheel's velocity. Degree of mobility equals 3 minus number of independent kinematic constraints. So the independence is important in this definition. The degree of mobility quantifies the controllable degrees of freedom of a mobile robot based on the change applied to wheel velocities. If the controllable degrees of freedom is equal to total degrees of freedom, then the robot is said to be holonomic, non-holonomic otherwise. Let's take an example. This drive robot has two standard wheels, but they are on the same axis. So they are dependent in terms of their lateral slip. So number of constraints is 1, and degree of mobility equals 3 minus 1 based on this relation. So degrees of mobility is 2 for a diff drive robot. This implies that the robot can alter x dot r and theta dot just through wheel's velocity, and it is impossible to alter y dot r instantly. XR and YR here are axes of body coordinate. As another example, consider a bicycle robot which has two independent wheels. So there are two constraints, and degree of mobility equals 3 minus 2 equals 1, and this robot can just alter x dot r using wheel velocity, and it's not possible to alter x dot y dot r and also theta dot. Let's talk now about the degree of steerability. Steering has an impact on how the robot moves. The degree of steerability is the number of independent steerable wheels. And in this definition, only centered orientable wheels are considered. Note that a steerable standard wheel will both reduce the degree of mobility and increase the degree of steerability. For example, in a bicycle robot, one wheel is steered, and therefore delta is equals 1. Let's recap the notion of maneuverability. In general, the maneuverability of a robot depends on the number of independent kinematic constraints. It's mathematically the summation of the degree of mobility and degree of steerability. This index is an indication of how easy it is for a robot to move around. You will see next that two robots with the same degree of maneuverability are not necessarily equivalent. Here you can see two robots with the same degree of maneuverability. For the diff drive robot, delta S is 0, delta M is 2, and delta M, the degree of maneuverability is 2. And for the bicycle robot, the degree of steerability equals 1, degree of mobility is 1, and degree of maneuverability is 2. Let's compare the degree of maneuverability with the number of DOF in the environment, the degrees of freedom. As you know, the degrees of freedom of both robots are 3, and the degree of maneuverability of a diff drive robot is 2. It has 2 degrees of freedom that can control directly, but yet it can position itself anywhere in the plane. The degree of maneuverability of a bicycle is 2, and it only has 1 DOF that can be directly controlled, but as you know, it can also position itself anywhere in the plane. You can see more examples in this slide. In the robot on the left figure, figure A, which is an omnidirectional robot, degree of mobility is 3, degree of steerability is 0, and degree of maneuverability is 3. It has 3 ball or spherical wheels. These wheels do not impose any constraint. In figure B, the robot has 2 simple wheels. They are not steerable, and one spherical wheel or omni wheel, and delta S is 0, degree of mobility is 2, because there is one constraint here, and they are not independent. So the degree of maneuverability is 2. In this robot, which has 2 omni wheels and 1 steerable wheel, the degree of steerability is 1, the degree of mobility is 2, because here we have a constraint on the motion on the, in the sideway. So the degree of mobility is 3. In tricycle, degree of steerability is 1, degree of mobility is 1, because we have 2 constraints on the sideway motion, one here and another here. So degree of mobility is 1, and degree of maneuverability is 2. In this robot, also the degree of steerability is 2, because they are independent, and degree of mobility is 1, because we can write 2 constraints on sideway motion here. So the degree of mobility is, degree of maneuverability is 3. And in this robot, which is a Sergio bicycle with 2 steerable wheels, the degree of steerability is 2, and the degree of mobility is 1, and the degree of maneuverability is 3. Here we have 2 steering wheels on different axles. And two constraints are here, so the degree of mobility is 1. We can also determine the type of robot based on the degree of mobility and degree of steerability. In figure A, all the wheels are caster wheels and don't impose constraints. So delta M, the degree of mobility is 3. And there is no centered orientable wheels. So degree of steerability is 0. And the type of robot is 3, 0. In figure B, there is no centered orientable wheels, and there is just one constraint, because the constraint of these two wheels are not independent. So the degree of mobility is 2, and degree of steerability is 0, and the type of robot is 2, 0. In figure C, which is a car-like robot, there are two mutually dependent centered orientable wheels, and degree of steerability is 1. As similar to diff drive robot, the delta M is also 1, so the type of robot is 1, 1. If in the figure D, we have just one centered orientable wheel, so the delta S is 1, and there is just one constraint on sideway motion, so the degree of mobility is 2. And in figure E, we have two mutually independent centered orientable wheels, so the delta S is 2, and the degree of mobility is also 1. In figure F, all the wheels are mecanum wheel, so they don't impose constraints on the degree of mobility, so the degree of mobility is 3. And there is also no steerable wheel, so the type of robot is 3, 0. The degree of mobility quantifies the controllable degrees of freedom of a mobile robot based on the chains applied to wheel velocities. If the degree of mobility is equal to the total degrees of freedom, then the robot is said to be holonomic. An holonomic robot, like this robot, can directly control all velocity components. Think about the degree of maneuverability of these robots, as well as degree of mobility and steerability. In the next lecture, after talking about instantaneous center of rotation and instantaneous center of curvature, we will derive the kinematic equations of several wheeled robots. Thank you.